Hello, hello. Welcome everybody to Modern Mathematical Methods for STEM Majors. I'm Dr. Richardson, and I'm really excited to help you learn all these mathematical concepts that are going to help you not only in just calculus, but in your STEM career and beyond. If you are taking my personal section of Math 6 and you missed day one, please go watch the previous lecture, Lecture 0, just to give you kind of an intro about the class. This lecture is the first content lecture, so let me go ahead and pull up the slides and we'll get started. All right, so we're in section 1.1, and I want to start with just a chapter 1 overview. These are all the sections in chapter 1. Section 1.1, what we're doing today, is all about fundamental intuition. I'll get into that in a minute. The next section is 1.2, which is really just about some important number sets, things like natural numbers, integers, rational numbers, the real numbers. We're going to talk about those and maybe refresh your memory about what those sets are. Section 1.3 is all about decimals and estimation. Having a good, strong understanding of the decimal system and being able to estimate is a very powerful mathematical skill, so we want to review it here. Section 4 is an important one. That's all about the theory of approximation. A lot of modern mathematical concerns and scientific concerns are related to approximations and how to get better and better approximations, or approximations that are just what you need, I'll say. Section 1.5 has kind of a silly name, algebra plus geometry equals BFFAE, because algebra and geometry really are just best friends forever and ever. We'll get to that. Last section is section 1.6, and that one's all about expressions, equations, and inequalities. That's a section where we finally do some of the more rigorous algebra. The previous sections are more building numeracy and mathematical intuition, which I'm going to talk about right now. So the first section, or this is this section's overview. We're going to talk about intuition versus rigor. We're going to go through some fundamental intuitions of things, in particular, fundamental intuition of addition, subtraction, multiplication, exponentiation, division, and just to give you some more fundamental intuition about fractions, because we use fractions a lot. And in my experience, personally and professionally, a lot of people are really afraid of fractions or just kind of cringe when they see fractions. I know I did when I was an early and a younger math student, so hopefully I can help you work through those feelings as well. But let's talk about intuition versus rigor to start. So, when we're learning and doing math, there's two important characteristics of mathematical reasoning that we need to carry with us. One of them is intuition, and that's basically the ability to understand something from an instinctive feeling rather than a rigorous reasoning built from like a rigorous foundation. And then the complement of that on the other side is rigor, and rigor is the quality of being extremely thorough, exhaustive, or accurate. So there's a play that goes on between these two when you do and you learn math. Mathematical intuition is critically important. It's important in math and science in general, but it's not sufficient as an acceptable foundation for science. And that's kind of the catch. You might have a gut feeling about how something should be, and you should lean into that feeling to help guide you and make you think about what to do next. But unfortunately, you can't build science off of that. And that's where rigor comes in. So yeah, intuition is a helpful guide. It allows us to make sense of things and make meaning. But if we want to carry the truth, we need rigor. So rigor is a necessary part of doing math and science. But here's the catch. The act of being rigorous a lot of times will hide the nature and the meaning of the ideas we explore. So you don't want to be only rigorous and you don't want to be only intuitive. You want to blend the two to help guide you in your discoveries. Yeah. Oh yeah, here's a blog post I recommend you all check out. It's by Terrence Tao. He's considered the greatest living mathematician. He works in the UCLA math department. I think he's still the chair of that department, but he wrote a really good blog post called "There's More to Mathematics Than Rigor and Proofs." Where he talks about the different stages of mathematical education, the pre-rigorous stage, the rigorous stage, and the post-rigorous stage. So every student of mathematics goes through these three stages. In this course, and in the calculus sequence, you're going to be learning how to make the transition from the pre-rigorous stage to the rigorous stage. And because of that, there's going to be an emphasis on intuition in this course. Rigor is going to be required, but I want you to continually ask yourself those questions that we talked about on day one. What's the intuition behind this? Why does this make sense? Why am I learning this? Why is this important? Those are questions you want to have at the forefront of your thoughts. Um, and as you make your way through this course and your lower division undergraduate courses, you'll notice that your ability to apply rigor to your mathematical ideas will improve as you become more of a scientist. That's kind of the journey to becoming a scientist. So we're going to start by establishing some fundamental intuition for some basic mathematical operations and some concepts. You've likely seen these before, but it really, really does help to bring them to the forefront again because you'll be surprised at how much you can rely on these basic intuitions to help guide more complicated ideas. I'm not trying to be patronizing. If you know all of this already, then that's great. I'm assuming you don't know any of this. So don't feel bad if you've never heard any of this stuff before. That's why we're talking about it right now. Yeah, and this is the big thing. When you get stuck in the sense-making process, think back to these fundamental intuitions that we're talking about right now in this section. So first one is addition. Just what is addition, basically? The meaning of addition, it just means to bring together or to combine, and we denote that process with this symbol, the little cross symbol right there. So whenever you see this cross symbol, I want you to picture bringing two collections together to form one collection, and we call that result, that combined collection, we call that a sum, and that's what we mean by that symbol, addition, and the word sum. And here's just kind of a visual picture of it. If you're using the fill in notes, you can kind of fill in what's going on right here. There should be a blank spot where you can fill this in. And again, I know this is very basic stuff, but it helps to just go through it and make sense of what's happening. Here I have two collections, right? I've got two things and I've got three of the same things and I'm combining these two and these three things to make a total of five things. This is what addition looks like. So when you have these objects like this and you bring them together, that's addition. This is the sum, and obviously the sum of two and three is five. There you go. Now let's talk about subtraction. So subtraction means to take from or to remove. And we use this symbol right here, the little horizontal line symbol. So whenever you see that symbol, I want you to picture removing a chunk of something from something else, taking something out of something else. And what remains after you've removed that piece, that's what we call a difference. So when you hear that word difference, it's the result of a subtraction. It's like what you're left with after you take the thing away from the other thing. Here's another picture of this. Again, I know this might seem very basic, but it's good to review it. Here, I'm starting with eight objects. I'm starting with the number eight. Each one of these squares is a one. So altogether, I've got eight of those ones. And here I'm taking away two of those ones. I'm subtracting two. So when I start with eight and I take away two, I'm left with six. And that's what subtraction is, taking something away and what you're left with. So we say that the difference between 8 and 2 is 6, the stuff that's left over, right? Okay, now let's talk about multiplication. So, what is multiplication? Well, when whole numbers are involved, multiplication is really just repeated addition. It's adding something a certain number of times. You're repeatedly adding the thing a certain number of times when whole numbers are involved. We denote multiplication by this little cross symbol or just a simple dot. And that's the dot is mainly just to save us a lot of messy notation. So you'll see either of those two symbols used. Whenever you see those two symbols, what I want you to do is I want you to think about a quantity being repeatedly added to itself, okay? And we call that a product. So the result of a multiplication is a product. Um, this is actually why we use the word times. Oops, get back, hey, come back, come back. There we go. This is actually why we use the word times when we talk about multiplication, because you're adding a number a certain number of times. Okay, so here's a couple of examples. What is 3 times 6? Well, it's just adding 3 6 times. What's 14 times 5? It's adding 4, I'm sorry, adding 14 5 times. 1, 2, 3, 4, 5. Or how about when you see this? When you see something like 8x, that means to add x 8 times. Is that 8 times? 4, 4, that's 8 times, right? So when you see these types of things in algebra, which we will, think about it as adding x 8 times. Now, things get a little more complicated, obviously, when products of two or more irrational numbers are involved. We'll talk about those in the next section. So this interpretation of repeated addition doesn't quite hold because it doesn't really make sense to add something like pi many times or root 2 many times. But this idea of repeated addition or just kind of doing that thing a bunch of times is still very helpful for intuition if you just allow yourself to imagine adding a quote fraction of a time or just repeatedly adding the same quantity but adding fractional quantities, right? Again, that is not rigorous, but it is very helpful for intuition. Moreover, multiplication, these two operations, multiplication and addition, they're continuous operations over the real numbers. So that means they're well defined no matter what numbers are used. You can multiply two irrational numbers, you can multiply a whole number and an irrational number. You can multiply any real numbers in a very smooth and continuous way. So it all makes sense in the end. So another important interpretation of multiplication is this. We're going to see this more later. Multiplication stretches or compresses quantities, right? So like before when I had 8x, you can think about 8x as taking the number x and stretching it by a factor of 8, stretching it to 8 times whatever x is, right? So depending on what x is, you're going to stretch it 8 times, right? We'll use this a lot when we explore vectors, transformations of functions, and exponential functions. Um, this interpretation expresses the continuous nature of multiplication better because repeated addition is inherently a discrete process. Discrete meaning like you can cut it up into little chunks, right? Continuous is smooth, unbroken in some sense. Here's another cool thing about multiplication. I don't know if any of your teachers told you this before, but multiplication can always be pictured as a signed area. Any product can be written as an area. Any product at all, any of it whatsoever, you can represent it as an area, which is a very powerful interpretation. So here's an easy example. 3 times 6, you can view it as the area of a rectangle that has side length 3 and side length 6. And if you multiply those two things, you can kind of think of it as repeated addition in this case because they're both whole numbers, right? So here's 3. And what we're going to do is we're going to add 3 6 times. Ready? Here's 3, 1, 2, 3, 4, 5, 6 times. So if I add 3 6 times, what do I get? I get 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There we go. So that's a way of interpreting it, right? How about something more like this? Here's pi times 2 pi, which is equal to 2 pi squared. Well, check this out. If this is pi, and this is 2 pi. Well, half of 2 pi is 1 pi, right? Half of 2 is 1. So this length is pi, this length is pi. So this is pi squared. Pi times pi, pi squared. That's actually why we call it square, because it makes a square if you view it visually, or if you interpret it visually or pictorially, right? So here's pi squared, here's pi squared. I have two pi squareds. There you go. 2 pi times pi is 2 pi squared. Okay, now let's talk about exponentiation. Before we get to division, let's talk about exponentiation. So when whole numbers are involved, exponentiation just means repeated multiplication. It means multiplying a whole bunch of times, multiplying something over and over and over again. It's repeated multiplication. And the way that we denote exponentiation is with a little superscript. So I'm assuming you all have seen this before. Let me zoom in real quick, right? Oops. Ah, all right, I got to work on that. Hey, come back, come back. There we go. That little superscript right there. So whenever you see a superscript used, what I want you to do is I want you to picture the number the exponent is attached to, the base, being multiplied that many times. Okay? So whatever the exponent is attached to, directly touching, it means to multiply that base b by that many times, right? So if n is a whole number, b to the n just means b times b times b times b times b n many times. Okay? So for example, 2 to the sixth, multiply 2 6 times. And when you do that, you get 64. The result of an exponentiation is called a power. So we call this the sixth power of 2. That's 64. Right. Another really helpful interpretation of exponentiation or just an exponent is you can think of an exponent as, quote, counting factors of the base, right? So let's look at it through a simple example. 2 to the 6 means there are 6 factors of 2. We're going to talk more about factors in, a little bit of a later section in this chapter. But 2 to the 6 means you've got 6 factors of 2. X to the fifth means that you've got 5 factors of x, right? One, two, three, four, 5. That's x to the fifth. Square root of 3 to the 2 means that you've got 2 factors of the square root of 3. So square root of 3 times square root of 3, that equals to the square root of 3 squared, which also happens to be equal to 3, as we'll see later on in the course. Okay. Um, so just like with multiplication, when the exponent is not a whole number, this interpretation doesn't quite make sense. It doesn't because of the discrete nature of repeated multiplication. Dit, you need that discretization. But again, exponentiation is a continuous operation, so it's well defined no matter what numbers you use. And if you interpret exponents as counting factors, or maybe a better word is indexing factors, it can really help a lot when we're working with rational exponents, things that look like this, right? Think of something like x to the 1/2 or 4 to the 3/8 or something like that. So when you see those types of things, you can still kind of use your intuition and think of it as saying, oh, I have half of a factor of x, or I've got 3/8 of a factor of 4. And you can use your intuition to operate on these types of numbers in a meaningful way. All right, we'll see that in chapter 4, first section. Okay, now let's talk about division. So there's a lot of different ways to interpret division. When whole numbers are involved, division is repeated subtraction. So again, you can think of division as repeatedly taking out something, right? Multiplication was repeated addition. Division is repeated subtraction, taking out, taking out, taking out, taking out. And we use this symbol, this little, this one right here, that symbol right there, or we'll use a fraction bar. Oops, I got to work on my zooming here. Or we can use a fraction bar. So symbolically, we have a divided by b equals a over b. And this is intentional. This is to basically suggest. So this little division symbol, you can think about it as a goes in the top and b goes in the bottom, and you get a over b. There you go. So that's what a divided by b means. So whenever you see that, you can think about the quantity b being repeatedly removed from a. So for example, 18 divided by 2 means how many times can you subtract 2 away from 18? And you can just count, right? You go, okay, 18 minus 2 is 16, minus 2 is 14, minus 2 is 12, minus 2 is 10, minus 2 is 8, minus 2 is 6, minus 2 is 4, minus 2 is 2, minus 2 is 0. How many was that? 9 times. Sorry, I'm holding like a pencil here, so 9 times. There we go. Now, the result of division, the quantity itself, we call that a ratio. This is the ratio of A and B. So that's what that word ratio means. Now, here are some important meanings, important interpretations of that symbol A over B, and we're going to lean into these a lot during this course. So I strongly encourage you to make sense of these ideas and to use them to guide your intuition. Um, Again, it's not fully rigorous, but it will help guide you when you are working with these types of symbols. So here's an important interpretation. This symbol A over B means how many times does B fit inside of A? Or how much of B fits inside of A? And this symbol, A over B, represents that number of times or that amount of B. So, I just want to pause here. I want you to think about this, like I was talking about in the intro lecture. Just pause and think about this for a minute, right? Now I want you to say these out loud. And remember, you don't have to say it to anybody. Just say it to your computer screen or to your dog or to your friend or to your parents or to your hand or to your feet. It doesn't matter who you say it to. Just say something out loud to give your brain that feedback. All right? Okay, so let's play around with this a little bit and try to make sense of it a little more. So for example, think of the number 3 halves or 3 over 2. 3 over 2 means how many times does 2 fit inside of 3? Well, try counting it. Okay, if I've got 3 and I try to cram 2 into it, okay, 2 will fit in there one time, but then there's a little bit left over, right? So 2 will fit in there once, but then there's one left over, and I can't fit a whole 2 into one. I can only fit half of a 2 into one, right? Because one is half of 2. So that means I can fit 2 into 3 one whole time, and then half of another time, quote unquote, right? Half of another time. So in other words, 3 over 2, 3 halves, equals 1 plus a half, or in other words, 1.5. This is why 3 over 2 is equal to 1.5. It's really just counting how many 2's fit inside a 3, or how many times 2 fits inside a 3. Think about this. Let's look at a strip diagram. So ask yourself the same question. How many times does 2 fit inside a 3? Well, think about this strip diagram. We're actually going to play around with a version of these, a physical version of these in class called Cuisenaire rods. So let's just break this down. This strip right here represents the number 1. This strip represents the number 1. This strip represents the number 1. They're ones, right? And if I line 3 of them up together, I get 3. So this long strip is equal to 3. And now because I know how big 1 is our unit, I know how big 2 is. This is 2. So let's see how many of those 2's we can fit inside of 3 right here. Okay, well, here's a whole 2, right? And now if I try to put another whole 2 in there, it doesn't work, right? I can't fit another whole 2 inside of 3, but I can fit half of one. I can fit half of one. So here's one whole 2, and here's half of a 2. So how many 2's fit inside a 3? 1.5. That's how many 2's fit inside a 3. So you can visualize these things, and this type of visualization, you can carry it into even more abstract concepts. It doesn't have to be whole numbers or positive numbers or rational numbers or integers. You can extend these ideas to any real number, and it will really, really help you make sense of the stuff that we do later on, the more complicated stuff when you're like, oh my gosh, what's going on? I have no idea. Lean into these fundamental intuitions and they'll help guide you. Okay. Now, let's assume for a minute that A and B are both positive numbers. We can get some important intuition from asking the question, how many times does B fit inside of A? So think about this for a minute. If B is smaller than A, right? So the bottom part is smaller than the top part. Then this number, whatever it is, A over B, has to be bigger than 1. It's got to be bigger than 1 because I can fit B into A at least once, right? So if B is smaller than A, then I can fit B into A more than one time. So A over B is bigger than 1, greater than 1. Now, if B is greater than A, right? So B is the bigger number here, then A over B has to be less than 1 because I can't even fit a whole B in there, right? I can't fit a whole B into A. So A over B has to be less than 1. There you go. I can't fit B in there even a whole time. Now, if A and B are equal to each other, if A is equal to B, well, then A over B has to be equal to 1 because I can fit B into A exactly one time or exactly once. So that's why when these two numbers are equal and you divide them, you get 1 because you're fitting one number into itself and you can do that one time. So you get 1. There you go. So in other words, any non-zero number divided by itself is 1. Pretty cool, huh? I think that's cool stuff. Okay. Now, I want you to think about this one, okay? So we're going to answer this, and this is going to maybe blow your mind, hopefully, but let's pretend for a minute that x is greater than 0. It's a positive number, right? Positive real number. My question to you is, how many times does x fit into 1? In other words, what is 1 over x? Okay, so I want you to just think about this for a minute. Okay, now I want you to say something out loud. Doesn't matter what it is. You could even repeat the sentence. You don't have to say it to anybody. Just say something out loud. Okay, now what I want you to do is I just want you to write some things down. Pick some numbers for x, and then try to think about what 1 over x would be. you could pick the numbers like 2, 3, 4. You might want to pick some numbers that are smaller, though, some numbers that are still positive, but maybe small fractions. Try those. All right, now let's explore it together. Check this out. As X gets bigger, maybe you saw this yourself, as X gets bigger and bigger, the number of times that it fits into one gets smaller. So maybe if I drew like a little sketch, for example, here, we'll call that X. We'll just call this Y for now. But as X gets bigger, as X is getting larger and larger in size, well, the number of times that I can fit it into one gets smaller, right? Think about something like if like if X is 100, 1 over X is 1 over 100. That's a pretty small number, right? And if X is 1,000, 1 over X is 1 over 1,000. That's even smaller. Trying to fit 1,000 into one, that's very getting tinier and tinier, right? So as X gets larger, the number of times you can fit it into one decreases. It goes down, right? Ooh, what about if X is equal to 1? Think about that. What if X is equal to 1? Then what's 1 over X, right? So, oops, there you are. If X equals 1, then 1 over X equals 1 because you can fit 1 into 1 time. So when X is equal to 1, we'll say that's like right here, you can fit it in there one time. There you go. Okay, now let's pick numbers that are smaller than 1 in size, okay? Like, what if X is Here, let's do this. What if X is 1/10? Let's try that. So maybe I'll go up here and I'll say, okay, X is equal to 1/10. Well, then that means 1 over X is equal to 1 over 1/10. Okay, now don't fret. We got fractions and fractions here. I know that may leave like a bad taste in your mouth or trigger your anxiety. That's okay. That's a normal reaction. But remember what that symbol means. It just means how many times does 1/10 fit inside of one? Well, if it's 1/10, then I can fit 10 of those inside of one, and that will make a one, right? So 1 over 1/10 is equal to 10. Ooh, okay. So as X is getting smaller in size, the number of times we can fit it into one is getting larger, right? Let's do 100th, right? Let's do 1 over 100. X equals 1 over 100. So 1 over X equals 1 over 1 over 100th. Okay, but then that's going to be 100 because I can fit 100th into one 100 times. So 1 over 100th is 100. And here we go. As X is getting smaller and smaller, we can fit more and more of them into one. So it's going to increase as X gets smaller. There we go. And then lo and behold, that's actually the graph of y equals 1 over x for positive x's, right? Um, One thing, notice it doesn't make sense when x is equal to 0. We will talk more about that later, but that's kind of asking yourself, how many times could you fit 0 into 1? And there's an intuitive interpretation of that, but that's when things get really messy. That's when you start playing around with infinity, which is what calculus is all about. We'll play around with infinity too a little bit in this class, but that's one of the fun parts of calculus is playing with infinity. But there you go. There you go. See here, we just intuitively produced the graph of 1 over x by using these fundamental intuitions, the meaning of a over b, right? This is the fun part about math. You can use that intuition to guide you, and then you can work out the rigor to make sure that your intuition is valid, because sometimes your intuition won't be. We'll see that later. Okay, here's another important interpretation. We're going to see a few of these for fractions. A over B, it's equivalent to this as well. You can pull that A into the front, and you can write it as A times 1 over B. And this is going to be really helpful later on when we're doing more algebra, right? But if a is a positive integer, this just means add 1 over b a times. So for example, if you had something like 2 over 3, you could rewrite this as 2 times 1/3. And that means to add 1/3 two times. So I've got 1/3 and I add another third to it. I have 2/3. Voila. 2/3. That's where 2/3 comes from, right? Remember, addition is just bringing together. Um, Now, regardless of what numbers are involved, B is always going to be how many parts you're cutting the whole into, and A is how many of those parts you have. So even if you see some funky number like, oh geez, I don't know, 17 over 283, I can do better than that. 17 over 283 might kind of freak you out for a minute. That just means whatever the whole is, whatever we're calling one, the unit, cut it into 283 pieces and then take 17 of them. That's what 17 over 283 is. You could use a circle to represent the whole. You could use a strip to represent a whole. You could use this symbol here, this numeral one, to represent the whole, but that's what that means. Cut one into 283 pieces and then add it 17 times. 17 times 1 over 283. There you go. Okay. Now let's look at a strip diagram for this again. Let's think about the number 3/4. Okay, so 3/4, we can interpret it as 1/4 three times. So once again, here's our unit. There's the number one. We're using a strip to represent that. And we're going to cut it into four equal sized pieces. 1/4, 2/4, 3/4, 4/4. Oh, got ahead of myself. One, two, three, four. Okay, so if I cut it into four equal sized pieces, let's count three of them. One, two, three, and you get 3/4. This is the length of 3/4 as long as this is the length of one. So this is equal to three times 1/4, or 1/4 three times, right? There you go. So these strips can really help. The interpretation is still valid. Everything's all good. Now, here's another important interpretation. There's a bunch, right? But making sense of these fractions is really, really helpful. We can also think about it like this. So here, this time over here, we did this, right? A times 1 over B. Now we're going to think of it as 1 over B times A. And if you think about it like this just means you're taking 1/8 of the number A. That can sound weird, but remember, B can be any number. So if I had something like, oh, 6 over 15, you can think of it as, oops, 1/15 of 6. Incidentally, that's also why we like to use the word of for multiplication, because you're taking a fraction of a number. So this is 1/15 of 6. There you go. Boom. There you go. And this lets you think of it more as a stretching or a scaling, right? So you have all of these interpretations that are essentially, well, the result is equivalent, but the way they feel, the way they taste is a bit different. And that's where the intuition is so helpful. This one, you're really thinking of it more as a stretching or a scaling, 1/15 of 6, right? Okay. Now here's the cool part. We're going to see that these interpretations do actually give you the same result. For what we when we pardon me, when we were talking about 3/4, right? So 3/4, we can think of it as 1/4 of 3. Okay, let's draw out 3. Here's our unit 1. Okay, so here's 1 unit, 2 units, 3 units. Oh wait, sorry, my bad. This is 3. I didn't picture the unit on this one. So this whole thing is 3. Cut it into four equal sized pieces. One, two, three. So you get one piece, two piece, three piece, four pieces, all the same size. Now take one of those, because that would be 1/4 of 3. And this is what you get, 1/4 of 3. Now check this out. The interpretations give you the equivalent result. They are the same. Here's where I drew the unit 1. Here's 3 of those units to make 3. I cut the unit into four equal sized pieces, 1/4, right? Here's one, two, three of those pieces. So this is 3/4. But this is exactly the same picture we had from the previous slide. See it? Cool, huh? There we go. This kind of flexibility is extremely helpful when you're doing math, because when these numbers get even more complicated, these interpretations still hold, right? They still hold, and you can use them in really intuitive ways. Okay, now on that note, let's play. So I like to do activities in my class. I don't want to spend the whole time just like lecturing at you. I don't think that's as fun. So what we're going to do when we get to class is we're going to do a little activity related to this to let you explore these ideas and build that fundamental intuition. All right. As always, you can ask me questions. You can ask them in class. You can come to my office hours. You can email me. Thank you all for listening to this lecture, and I hope you enjoyed it. We got a lot more, and I hope you enjoy those too. Have a good day, everybody.